Take a look at this offshore production rig. Surrounded by miles of hostile, open ocean, the raw energy extracted here is completely useless. That is, until it can be moved. Human civilization faces a persistent geographic problem. The isolated pockets where we find raw oil, gas, and renewables rarely overlap with the dense population centers that actually need to consume them. To bridge that physical gap, we build energy corridors, coordinated bundles of infrastructure designed to manage massive flows between major economic nodes. This diagram illustrates a corridor's 4 mandatory components. Flow starts at the source, travels a route, passes transfer points, and reaches its destination. They must operate in unbroken synchronization. A single bottleneck at a transfer point causes immediate, cascading delays across the entire chain. Mastering this physical flow dictates the trajectory of modern economies. It determines exactly where heavy industry can be built and exactly how much raw power will cost. Maritime corridors facilitate the movement of the highest volumes of global oil and liquefied natural gas, or LNG. LNG is natural gas cooled to a liquid state to reduce its volume for easier transport. The sheer scale of these tankers allows a single vessel to carry millions of barrels across the open water, but sea routes are bound by physical geography. This map shows the Strait of Hormuz, the most critical transit choke point on the planet, measuring just 29 nautical miles across at its narrowest point. Zooming in, the navigable reality is even tighter. Ships are confined to strictly enforced 2-mile-wide inbound and outbound shipping lanes. Every single day, 20 million barrels of oil squeeze through that narrow space. That accounts for 25% of all global seaborne oil trade, alongside nearly 20% of the world's LNG. Maritime corridors offer unmatched capacity for volume, but their reliance on immutable geographic choke points creates a profound logistical vulnerability. If a strait closes, the flow stops. To bypass those maritime bottlenecks, engineers turn to land-based solutions, the pipeline corridor. A pipeline functions as an active, continuous machine, using massive artificial pressure to force dense liquids and gases across a continent. Take the East-West crude pipeline, also known as Petroline. This dual pipe system measures 48 inches in diameter and stretches 746 miles straight across the Arabian Peninsula. Moving up to 7 million barrels a day through that steel requires heavy mechanical infrastructure built along the route. These generators and compressors act as transfer nodes, actively pushing the payload forward through the network. Pipelines solve the geographic vulnerability of sea routes by engineering artificial physical paths through otherwise impassable terrain. The third physical network shifts the logistics from moving fuel to moving the generated power itself. This requires high-capacity lines suspended by massive, structurally engineered transmission towers. The core technological enabler for pushing this power across vast distances is high-voltage direct current, or HVDC. HVDC is a transmission method that minimizes energy loss over long spans, making cross-border power grids more efficient. The Great Sea Interconnector is a prime example of this logistical feat. This project requires the physical installation of 1,208 kilometers of thick 500 kilovolt subsea cables to link the power grids of Israel, Cyprus, and Greece. At both ends of that cable, engineers build massive multi-terminal converter stations. This sprawling infrastructure of cooling arrays and transformers translates the direct current back into alternating current, so it can safely enter the local grid. Electrical corridors eliminate the need for physical fuel transport entirely. They represent the most advanced, yet undeniably infrastructure-heavy, evolution of energy logistics. A highly resilient energy corridor requires 3 engineering traits: massive baseline capacity, physical redundancy through backup routes, and highly efficient transfer hubs. You can see that efficiency in the dense, interconnected piping of a modern processing facility. Because these systems guarantee reliable power, they generate a secondary economic gravity. Corridors do more than serve existing cities. They dictate exactly where new cities and industries are built. As a result, deep water ports expand, massive logistics zones emerge, and heavy manufacturing clusters build strictly along these engineered physical arteries, directly abutting the water for shipping access. We are seeing this historical infrastructure pattern repeat today with the emerging compute economy. Hyperscale data centers and AI processing facilities depend entirely on strict proximity to high-capacity electrical corridors. These networks are now layering on top of one another. As maritime lanes, pipelines, and electrical grids overlay, they create a dense global grid that pulses with constant flow. Economic leverage belongs to the nations that control these engineered paths. Power is found in the physical infrastructure that forces energy to flow.